One of the feature will be radius. So, so coming to types of antenna is broadly dividing into two types. One will be conventional antenna, the one will be smart antenna. So coming to conventional antenna, it can be dividing in, it can be varied with respect to different parameters. So first parameter will be according to frequency. So conventional antenna can be designed with respect to the frequency, that is first type. Second one, we can design radiation pattern. So either we can get circular polarization or linear polarization, or we can divert the radiation pattern into certain angle. That will be designing with respect to according to pattern. So next one will be according to surface current distribution. So we can design the antenna with respect to current distribution. So another thing will be according to size. So according to size also they can go for antenna, that is comes under according to size conventional antenna. And final thing will be according to number of elements. So number of elements means same as will be repeated for n number of times. That will be comes under array antenna. This is also one type of conventional antenna. So another type of antenna will be small. It can be broadly dividing into two types, adaptive antennas and fixed antennas. Adaptive will be simply we can say that adjustment. So based on the user requirement, we can adjust the antenna, that is comes under adaptive antenna. So this thing in nature. So next one, so based on the physical section. So just a minute. Sir, are you there? Sir, sir, I'm getting some disturbances, sir.
Okay, please, all of you mute yourself, please. All the participants, please mute yourself. Network problem or voice access, sir?
Voice వస్తుంది సార్ డిస్టర్బెన్స్ బ్యాక్ సైడ్ నాయిస్ వస్తుంది.
I will ask them to do it. Please, all the participants.
Now it is okay, sir. Now it is okay, sir. Okay. Thank you, sir. So next one, according to physical structure, the antennas can be broadly dividing into five types. First one will be wide antenna. It will be looks like a dish antenna. It comes under wide antenna. The next one will be planar antenna. So now the trend is towards the planar antennas only. Here we are discussing about number of antennas. So different antennas are there. Array antennas. I'm not audible. Okay. So am I audible now?
Yes, sir, you are audible, sir.
You can continue, sir. It's audible. But somebody is
Just a minute, sir. I will check my connection. So am I audible now, sir? Am I audible? Please respond anyone.
Yes, sir, you are audible, sir.
Now you are audible. I'm audible.
Sir, very much audible, sir. You can continue, sir. Sir, please continue.
Okay. So next we are discussing about physical structure. According to physical structure, it can be dividing into five types. One will be wire antenna. Another one will be planar antenna. Now the trend is going on towards the planar antenna. In planar antenna, so many types of antennas will become. So it will be either microstrip antenna or CPW antenna or SAW antenna and array antenna. So next one, we are discussing our aperture antenna. For certain applications, we are using aperture. Thing will be array based antenna. So array based antenna will be generally we are using for improving the gain or bandwidth. But complex of array gain antenna will be very high. So generally we won't prefer. If they require the gain, more gain, then only we are preferring about array based antenna. So what is mean by array means same shape will be repeated n number of times. That is called as array based antenna. Okay. So next, what are the trends going to antenna in India? So first trend will be bandwidth enhancement. So second trend will be axial ratio enhancement. And third trend will be gain enhancement. And fourth trend will be AWB antenna. So next one of the important metametric based antenna, CBC structure based antenna.
Hello, sir.
And dividing into two types.
Nothing much, sir.
One will be either in terms of frequency or either in terms of pattern. So it can reconfigure. That means we can switch one frequency to another frequency. That will come under reconfigurable antenna based on frequency. Another thing is
Sir.
so in terms of omnidirectional to bidirectional. So like that we can go for the reconfigurable pattern based antenna. So next one, diversity based antenna. So next trend will be SAW. This is the one of the trend now is going on India. Not only India, in abroad also the trend is going based on the SAW based antenna. So SAW means trusted integrated waveguide based antenna. So another thing will be dielectric resonant antenna. So next one MIMO based antenna. That means multi-input, multi-output based antenna. And one of the more important trends is wearable antennas. So we can wear the antennas for security purpose, automatically we can transfer the information. Okay, so either we can use textile materials or we can wear them. So like that methods we can use it for developing about the wearable antenna. So one more trend will be leaky wave antenna, lens antenna, antenna, terahertz and impulse based antenna. So among these all those trends, so very important trend will be MOT antenna and metameter based antenna, antenna for cognitive radio, SAW based antenna, Delta resonant antenna, MIMO based antenna and wearable antenna. So MIMO based antenna and wearable antenna.
సార్ కొంచెం మీ దగ్గర నెట్వర్క్ ఇష్యూ ఉన్నట్టుంది కొంచెం బ్యాక్గ్రౌండ్ నాయిస్ వస్తుంది నందకుమార్ సార్
So next one, antenna parameters. So antenna parameters, so it can be designed with respect to two ways. One will be structural, another one will be functional. Right. If we come to the structural means the shape of the antenna. This can be based on three parameters. One will be what material we are using for designing about the antenna. So generally, if we want to design about the antenna, we require two parameters. One will be substrate, another one will be conductor. So next one, what is the material constant? So this comes under direct constant values of the substrate as well as the conductor. So final thing will be dimension of the antenna. So width and height of the antenna. These three parameters are comes under section of the antenna parameters. So if we come to the functional, we have to discuss about what are the parameters existing in the antenna. So we have to evaluate VSWR, reflection coefficient, gain, efficiency, bandwidth, axial ratio, and group theory. So if we come to the VSWR stands for voltage standing ratio. So if the definition of VSWR is what? Is the ratio of maximum to minimum voltage on lossless line. Okay. So next one, reflection coefficient. So reflection coefficient means, so it is the ratio of the reflected wave to incident wave. So based on this fact, we are deciding that how much information can be received from source to destination. So then another thing will be gain. So ability of antenna to radiate and collect electromagnetic energy comes under gain of the antenna. So efficiency can be divided into two types. One will be radiation efficiency and total efficiency. So coming generally we are discussing about radiation efficiency in the case of antenna. So radiation efficiency will be ratio of power delivered to the antenna relative to the power radiated from the antenna. Okay, these are the very important functions. After designing we are evaluating. So another thing will be bandwidth. So already everyone knows that. So bandwidth is the difference between upper and lower cutoff frequency. Okay. So next one, how the era of the microwave will be started. In 1950s, the new era of microwave semiconductor device technology was started. So it is rapidly progressing for developing about the microwave semiconductor device, and finally it was started in 1965. The microwave semiconductor device will be SIP transmission line. The father of SIP transmission line will be Barrett and Strand. Second transmission line will be microstrip line. So it got introduced by Garrick and Engelmann in the year of 1952. In 1916, we have started in 1915. Well, sorry, in 1916, we have started about the integration of planar transmission. So planar components means all are fabricated in a single chip is called as planar transmission. In previous days, we are designing different components. Finally, we are connecting. That will be replaced with the planar transmission. Okay, in 1968, another transmission line will be introduced. That will be slot line. The father of the slot line will be as big con. So in 1969, we are going for the CPW that is introduced by CP. Plane CPW means here the radiation loss will be somewhat high. So to overcome that, we are going for CPW. But the power handling capacity of the CPW is also very high compared to microstrip. So in 1970, we are going for next transmission line, that is spin line. It got introduced by Mir, and finally 1999. Just a minute. So I'm audible now. Please respond anyone. I'm audible clearly.
కొంచెం బ్యాక్గ్రౌండ్ వాయిస్ వస్తుంది సార్ మీరు
So please respond.
సార్
So Srinivas, I'm audible clearly, sir.
audible but there is some background noise sir from your side. ప్రొసీజర్ సార్ ఒక సౌండ్ వస్తుంది వాయిస్ వస్తుంది. Right, don't they send no voice now? Continue, sir. No. Again,
So these are the different planar antennas existing in microwave. The first line will be strip line. So how we are designing strip line means we have to consider one substrate. In top of the substrate will be ground plane, bottom of the substrate will be ground plane. In between we are assigning the strip. The width of strip will be W. This is the shape of the strip line. So next one will be micro strip line. So we are placing on top of the substrate with the width of strip and bottom will be ground. This is the shape of the micro strip. So another thing will be slot line. So in slot, we don't have the ground plane on the bottom of the substrate. We are having one slot. This is slot. So in two directions we are placing ground plane. So in between slot only we are transferring up an information that is inside the slot. So next one, discussing about coplanar waveguide. So we are having this is slot, this is strip. Strip is having some spacing. So after that we are placing over the ground plane. So this is positive, these two are the negative. So next one, coplanar strips. So these ground planes are up to till end, but here we are spacing some space. This is called as coplanar strips. This is the standards of the planar transmission line. So next one we are discussing about microstrip patch antenna. Okay, so microstrip patch antenna will be invented by Bob Monson in 1972. If we come to the shape of the microstrip antenna, we are placing patch will be on top of the substrate and bottom will be ground plane. Okay, so for having about good performance, we have to use about the fixed plate. and lower dielectric constant. So already we know that F is indirectly proportional to 1 by root ER. So we need to get about the more bandwidth automatically, dielectric constant will be very less. So if we are maintaining all those conditions, automatically it will maintain about the better efficiency and better radiation and larger bandwidth. Okay. So in generally, this is called as printed antennas. So mostly preferred for micro frequency only. So in general, microwave frequencies are up to 3 gigahertz to 30, but microstrip antennas will be preferred up to only 6 gigahertz only. So more than that also we can use, but won't get the better efficiency as well as the larger bandwidth. Okay. So because of size, the antennas radiation will be depend upon antenna radiation depend upon guided wavelength. So generally we are preferring for narrow band and narrow beam antennas only. We are not going for the wide band antennas. This is the simple overview of the microstrip patch antenna. So what are the shapes we are using in microstrip? So we can prefer either rectangular, shape, square, circular, angular ring, and elliptical or triangle. This is the basic shapes we are introducing in starting 1970s. Now the trend is going on towards fractal based antennas, metameter based antennas. So many antennas are introducing in the case of microstrip patch antenna. So what are the advantages if we go for the microstrip patch antenna? So it having very low profile and easy to fabricate because we are having only substrate as well as the patch. So we can easily fabricate the antenna. The cost of the antenna also very less. We can easily connect with the different feedings. Either we can choose by coaxial cable or microstrip plane or fin line. So easy to incorporate with some other elements of the microstrip antennas also. It will gain of the antenna will be around 6 to 8 dBA. So in wireless communication, 60 dB bandwidth is sufficient. So we can easily, if we need to increase about the gain of the antenna, so we can use about the array-based antennas for increasing the gain. Which is the advantage of the microstrip-based antennas. So coming to drawbacks, it having low bandwidth. So if you need to require about more bandwidth, we can go for different techniques. Automatically we can improve the bandwidth. So one of the important technique will be we can go for array-based antennas. So by using array-based antennas, we can automatically increase the bandwidth also. So one more thing will be already we know that substrate thickness will be proportional to the bandwidth. So automatically if we increase about the height of the substrate, we can increase about the bandwidth. That is the one of the important drawback. Okay. So next one will be efficiency will be lower compared to all other antennas. So why efficiency will be low means it is open space. So we can transfer the information via open space automatically. If you are feeding the antenna by using microstrip or coaxial feed, so the antenna will be radiated in open space. So automatically some loss will be occurs due to conductor as well as the dielectric losses. So because of this reason, the efficiency will be somewhat less in the case of microstrip antenna. Okay, so one more thing will be we are preparing only microwave frequencies and above. We are not requiring about the low frequencies. So if you go for the high frequencies, automatically substrate becomes too large. So generally go for high frequencies also. Okay, so it can't handle about the high power. That is the main drawback of the microstrip antenna. For these reasons only, we are going for the next planar antenna. That is planar waveguide antenna. Okay, these are the advantages. So applications, we can use it for satellite communication, we can use it for microwave communication, we can use it for cell phone antennas and also local positioning system antennas, GPS antennas. These are the different applications existing in nature. So one will be mobile and satellite communication, GPS, direct broadcast, RFID, WiMAX, as well as the wireless. So in all these cases, we are using about microstrip antennas. why we can prefer microstrip antennas? Is there any specific regions? Yes, we have some regions. So if you consider about flat, we are having about flat microstrip patch antenna. You can easily mount it on the top of the airplane. So we can automatically perform the air communication by using microstrip antennas. So impedance matching is a very, very important parameter in the case of electromagnetic frequencies. So this can be easily done by using the microstrip antennas. So having very small equations, with help of class equations, automatically can perform impedance matching. So if we are not getting impedance matching, automatically some information lost while connecting to some other devices. So next one, quality factor. So quality factor of the microstrip patch also very high. Due to this reason, we are preparing about microstrip patch and so remedies. So what are the remedies we are using for some losses? Okay, so already we know that microstrip patch are having less gain as well as the low power handling capacity. For this region, we can go for array-based antennas. So by using array-based antennas, automatically we can improve the gain as well as we can improve the power power handling capacity. So one more thing will be we are having already pure efficiency and also gain will be reducing and radiation patterns also reducing. This also we can improve by using about survey wave association. So with help of these techniques, automatically we can improve all those things. So one more thing will be, so this will be narrow band, that is low bandwidth. So bandwidth also we can increase up to 60% to 60% by implementing based on about array-based antennas, or we can go for fractal antennas, or we can go for metal-based antennas. So while introducing all those antennas, automatically we can increase the bandwidth as well as we can increase the size of the antenna also. These are the remedies we are considering while going for these antennas. So, what are the feeding techniques existing in microstrip antenna? We are having 6 feeding techniques. One will be coaxial feed, another will be microstrip feed. So, third thing will be proximity coupled microstrip feed. Fourth one will be aperture coupled microstrip feed. Fifth one will be coplanar waveguide, and final thing will be a line feed. So, we are not choosing coplanar waveguide and line feed. Why? Because we are discussing in only microstrip batch. So first one, coaxial feed. So this is antenna, right? So this is antenna. So we are placing the patch on top of the substrate. Bottom will be ground plane. So we have to radiate the information by using this patch only. This will be connected by using coaxial feed. So we are etching one drill that is connected from top patch to bottom patch. We are inserting the connector. From that, we are transferring the information from patch. This is the shape. This is antenna, microstrip antenna. This is bottom ground plane. This is top ground. This is patch. So we have to radiate the energy by using coaxial feed. So we have to drill the hole that is connected with ground to bottom. So after connecting, it will be radiated via patch. Okay. So generally, so where we are inserting the hole. So this will be most commonly. So middle y is equal to W by 2. So total width in half only we are inserting about the point for effective radiation. Okay. Suppose if we are not choosing exact this point, we are getting some disturbances in radiation as well as most frequently we are choosing about the middle point, that is W by 2 with half. Okay, this is the general scenario. This is the general scenario of the patch. So this is width of the patch. This is the length of the patch. So length of the patch will be indicates for flow of radiation or flow of current that comes under surface current. So length will be indicates, or width will be indicates for resonant frequency or fixing about the resonant frequency. In general, if we consider about the patch, the width will be somewhat high compared to the length of the patch. This is the matching we are doing while inserting about the coaxial feed. So already we know that this particular substrate having some resistance value. Okay, so that is comes under H. After inserting this comes under H. So from that we are finding about the final R value. So based on that only we are performing about the impedance matching. Okay, so next one, advantages and disadvantages. So it is very simple. We can easily fill the hole. Automatically we can connect the connector for transferring the information. So it is directly compatible with the coaxial cables. So we can easily adjust the position for getting about the exact results. So the advantages in the case of coaxial feeding. Okay. So next one we are discussing about disadvantages. So if having very less substrate, okay, it is very difficult to drill. So while drilling, it will be connected to parts are directly connected. This is the main problem. Okay. So suppose if you are changing the position automatically, what will happen? It will vary about the bandwidth also, and also it will limit about the bandwidth. It is the another problem. So it is not compatible with arrays. It is suitable for only single patch. If you are repeating more number of patch, it is not suitable. Next one, insert feed. So insert feed is the very, very important feed. Very easy in microstrip line. So this is the patch. That patch is connected with the microstrip line. Okay. This is very, very simple technique, and also it will having about planar feeding. So you can automatically use it for the arrays also. You can simply match it with the impedance matching. So these are the main advantages of the insert feeding. So disadvantages will be to significant line radiation for thicker substrate. So in thicker substrate, we are not getting exact bandwidth. That is the main drawback. So one more thing will be we are not getting exact radiation and patch current while substrate will be very small. Okay, for each and every designing, we have to choose the minimum height of the substrate. It will play the very important role. The next one will be proximity coupled field. So another name of the proximity coupled field will be, we can say that electromagnetically coupled field. So advantages will be what? Planar feeding. We are having less radiation line compared to microstrip feed, and also we are providing about the higher bandwidth. So if you observe this, actually we are having substrate. So in substrate also we are having two types. One will be single layer substrate, another one will be double layer substrate. Single layer means we are having one side ground. Double layer means we are having two side ground. Okay. So this is one substrate with having patch and microstrip. For connecting through, we are etching the substrate and we are inserting the microstrip. Okay. There is no connection between these two lines. So for this case, we have to go for the multi-layer fabrication. That means we have to add more number of substrate. In one substrate, we are placing about the microstrip plane. In another substrate, we have to place about the patch. Okay, so very difficult to perform the matching. So we have to run the alignment process for perfect matching. This is the main drawbacks in the case of proximity coupled field. So final thing will be aperture coupled patch. So same thing, it also allows planar feeding only. So planar feeding line radiates in the isolation patch radiation. So it also having multi-layer function. In top we are having in top we are having patch. In bottom we are having microstrip line. In between we are having about the slot line. So with this slot line we are radiating about the antenna. We are radiating using the patch. Okay, here also impedance matching is very difficult. That is the main drawback of the aperture coupled patch. One more thing will be when require more multi-layer fabrication. We are not using for the single substrate. We have to choose more than one substrate. That is considered the multi-layer. So by using this, automatically we can increase the bandwidth also. This is the main drawbacks and advantages of the aperture coupled patch antenna. So comparison of the different feeding techniques with respect to radiation and reliability, easy fabrication, impedance matching, and bandwidth. For all cases, almost we are getting 2 to 5% only, except proximity coupled antenna. So it having more bandwidth, that will be 13%. So impedance matching will be, every case it is will be very easy only, but somewhat difficult in the case of aperture coupled and proximity coupled. Why? Because we have to find out about the alignment process. If you are not aligning properly, we won't get about the impedance matching perfect. Okay, easy for application. It is very difficult microstrip line, but coaxial field because somewhat difficult. Why? Because we have to insert the feed by a substrate. So some sorting process is there and filtering process is there. In this case, fabrication process will be somewhat difficult. For this case, we need to consider about alignment. That is also incorporated in the case of easy fabrication. Reliability. So reliability, microstrip line, it is very reliable. So it is not that much reliable. These two techniques are good in the case of reliability. For comparing all those parameters, so microstrip line having better performance compared to all other feeding techniques. So generally we are going for the microstrip line feed. To support up to 6 GHz only. If you are going more than 6 GHz, we can use microstrip line only, but efficiency will be somewhat less. So coaxial feed is support for only up to 1 to 4 GHz. If we are going more than that also it will support, but we are not getting exact result. That means we are getting some radiation fluctuations and we are getting some efficiency fluctuations. So better we can choose for microstrip line up to 1 to 10 GHz. But for better results, we can choose up to 6 GHz. So this is the design parameter. It is front view and side. So front view, so this blue color indicates, sorry, green indicates for substrate. In that we are placing about the microstrip antenna, the microstrip patch antenna. This is the patch. This will be connected with the microstrip transmission line. Okay, in bottom, this is in bottom view. Bottom of the substrate will be connected with the ground plane and top will be patch. So like that we are designing about the antenna. For designing all those things, we have to consider about all design parameters. So we have a standard equation for designing about the microstrip transmission line. So length will be always we are choosing lambda g by 4. So in communication effective antenna length will be lambda by 4. In that we are having substrate, so we have to choose for the guided waveform. So we can choose lambda g by 4 multiplied by any integer. We can choose 2 into lambda g by 4, or we can choose 3 into lambda g by 4. We can choose 4 into lambda g by 4. There is no restriction on length of the microstrip line. But with the case, we have standard equation. Based on that, we have to finding about the width of the microstrip line. Okay, so already we are having a standard equation for length and width also. Okay, so in past nights we are discussing about length and width. Length is the direction of the current flow. Width is the resonant frequencies and higher bandwidth. So if we considering all those things, so width will be somewhat larger compared to length. So generally we can choose twice. Our maximum typical value will be we can choose 1.5 into L. So this is the typical condition. We can choose 1.5 into L. W is equal to 1.5 into length of the patch. So width plays a very, very important role while designing about the desired frequency. Here frequency of the microstrip antenna. So first one we have to find out about the F naught, that will be resonant frequency of the microstrip antenna. So C by 2 into effective dielectric constant EREF into M by L whole square plus N by W whole square by 1/2. So M and are the what the board we are transferring through the microstrip line. Okay, so based on that we are finding about the cutoff frequency of the microstrip line. Then we have the formula for finding about the width. So width is equal to T by 2 into F naught into square root of ER plus 1 by 2. This is the width formula in the case of microstrip line. So if you know the width, automatically you can find out the length also. Right? You can find out the length also, no issue. So substrate having dielectric constant value, but we don't know about the entire structure constant value. That will be effective dielectric constant. So that can be solved by using this equation. So the effective length also plays very important, So if we are not getting exact results, we can extend this batch to up to certain effective length. That will be calculated by using effective length. This is delta L. So this is the standard formula for finding about the delta L. So from that we can find out the length effective, that will be total length of the patch plus 2 into delta L. This is the standard equation for finding about the effective length of the patch angle. Okay. So we have another formula also for finding about the effective length. If you know the C, if you know the F naught, if you know the effective dielectric constant, we can easily find out the effective length of the microstrip. So one more formulas, we can find out frequency and bandwidth by using these formulas. These are the standard formulas existing while designing about the microstrip patch antennas. So coming to conclusion, so till now we are deciding about the general overview of the antenna and antenna parameters and planar technology, and also we are discussing about microstrip antennas and their feeding techniques. So already we know that microstrip antennas was invented by Baum Monson in 1970. So it will be designed with respect to printed technology. So one we are saying that printed antenna. Okay. So basic, we are, and also we are discussing about microstrip basic operations and what are the different feeding techniques existing in microstrip antenna. And finally, we are going to ending with the design equations. These are the conclusion. So I will mention some scope of feature work. For having different scope of feature work, so we can go for array-based slot antennas for best solution for improving the gain. If anyone are doing research in antennas, if you need to improve the gain, go for array-based slot antennas. So one more thing will be you can go for metameter-based antennas. So it will improve the gain as well as the bandwidth. So now trend is going on 5G in India. So we can implement the 5G technology based antennas. The range will be 24 to 28 GHz. So next we are discussing about we can for multi-band application, that will be dual and tri-band unlicensed band applications. So one more trend will be reconfigured antenna. This will be designing with respect to either frequency variation or pattern variation. So next one will be substrate integrated based slot antennas, and one more scope will be variable antennas. So variable antennas is trend is going on nowadays. Better you can go for variable antennas and texture based antennas. This is the scope of feature work and references for this one. Sir, any doubts? Srinivas sir, are you there?
Sir, I am here. Can you show any HFS examples already simulated one, sir? Sir, it is audible?
Hello?
Can you show any simulation your some design? Hello?
Sir, audible sir?
Ah, yeah.
Okay.
Can
Sir,
you
any
show
doubts?
can you show any simulation results of your design?
Okay, sir. I will tell you some important point for young researchers. After that, I will show one design, sir.
Because many students are interested to do the projects in this microchip.
Okay. Okay, sir. First, I will mention some important points. Then we will go for design.
Sure, sure, sure.
Okay. Thank you, sir. So next one will be basic points for young researchers. So what are the important factors while we have to use while designing about the antennas? So first one will be selection of the material. So while designing antennas, we have to, one important parameter will be selection of antennas. That will be in terms of substrate and also conductor. This substrate it can be divided into 2 points. One will be direct constant and loss tangents. So loss tangents is a very, very important factor. This we have to choose while designing about the antenna. So if loss tangent will be less, it will give some more accurate results. So these are the different materials existing in commercial elements. So we can go for artitorite, epsilon, alumina, ferrite, FR4. So like that we are having about the antennas with having different dielectric constants and loss tangents, RMS surface. So for high frequencies you can prefer artitorite antenna. So it will be support up to terahertz. But coming to FR4, it will support only 10 to 12 gigahertz only. We can design for up to 40 also. Some radiation effect is there. So generally, if you go for any literature of the antenna, we are choosing with the two materials only. One will be artitorite, another one will be FR4. Sometimes we are going for gallium also, but commercially available materials are artitorite and FR4. This is the very, very important parameter while designing about the antenna. The next one, with respect to connector. So before going to design about the antenna, we have to choose about the connector effectively. So connector is, first we have to select the connector. So there are different connectors. It is operating for different frequencies. So SMA connector, it will operate for up to 0 to 18 gigahertz. The diameter will be 7.9 mm. We are having K band, Ka band, B band. So diameter means the entire region up to white part is called as diameter. Okay, this is a simple example of the B band connector. It is ranges from 1.85 mm connector. It will operate up to 70 kHz. Suppose we are designing about high frequency, if we are connecting DNA connector, it won't support for we are getting the result. So we have to choose about the precaution of the connector. So next one, selection of the thickness. So selection of the thickness. So in the antenna, so this is the antenna, right? So selection of thickness will be considered substrate thickness as well as the copper thickness. These two are plays very important role. So if we are increasing the copper thickness, automatically we can get the results more. But automatically will increase the complexity of size. Automatically increase the complexity. So we have to choose the exact thickness which is suitable for our design. So and also we have to remember whether it is available in market or not. So one more thing will be copper. Sometimes we are designing with conductor. Sometimes we are designing with copper. Sometimes we are designing with silicon. Sometimes we are designing with silver. Sometimes we are designing with gold. Okay. Suppose in simulation, if we are designing with copper, if we go for the fabrication in terms of gold means the results will be fluctuated. So we have to incorporate all those things while designing about the antenna. So next one, with respect to radiation patterns. So with respect to radiation patterns means we are getting some beautiful results. This is reflection coefficient. We will be resonating exactly 60 gigahertz. Okay. So with respect to bandwidth, this will be very beautiful results. So if you go for the radiation pattern analysis, so it will be radiated uh, uh, after the zero axis. That means radiation patterns will be deviated. So we are getting some fluctuations. So if you are getting beautiful bandwidth also, if you are not getting perfect radiation, it is not suitable for some commercial application. So while designing antenna, not only choosing about reflection coefficient, we have to choose with respect to radiation pattern also. This is also one of the commercial element. So one more thing will be with respect to radiation efficiency. So with respect to radiation efficiency, so again we are getting about beautiful results. For this case, we are getting this is the efficiency. So if we observe this, this will exceed more than 1. That means more than 100%. That indicates for our designed antenna will be wrong. So we have to go for variation of the different parameters up to reducing about the radiation efficiency. These are the 5 important parameters we have to remember while designing about the antenna. Clear? Any doubts? Any doubts? Please respond. Sir, Srinivas sir. Shall we go for design? So these are the reference books. Those who are doing research, please follow these books. This will be helpful. So we are designing rectangular patch antenna for wireless communication at 6.5 GHz. Okay, this is the patch antenna. It having substrate and a patch and will be ground. So this is the parameters of the patch antenna. So we will implement by using this tool. We will stop sharing. So all of you please note it down. This will be helpful. So all of you please note down all those parameters. This will be helpful while designing about the antenna. These two. Let me know, is it visible my screen? Software is visible. Let me know. Yes, sir. Okay, thank you. So we can go for project template. So here we are having different areas. From that we have to choose microwave and RF and optical. In microwave and RF and optical also we are having different workflows. One will be antenna, and then will be circuit and components, and third one will be radar cross section, biomedical, optical application, periodic section. So in our case, we are choosing about antennas. Select antenna, next, press next. So one more thing, after selecting antenna, we are having different antennas. Waveguide, planar, wire, phase array, mobile phone integrated, reflector, director resonator, RFID. So go for planar. Why? Because microstrip will be planar antenna. So to select next. So select time domain. Don't go for frequency domain. So before going to start about the project, we have to check about the parameters. Dimensions, it will be millimeter. Frequency, it will be gigahertz. Time, it will be nanosecond. Temperature, Kelvin. Voltage, V. Current, amperes. Ohms. Conductances. So mainly we have to think about these two parameters. One will be dimension, other one will be frequency. So we are designing up to 6, right? We can go for 2 to 10. The middle frequency will be 6. So don't select all those monitors. If you are selecting all those monitors, it will produce the results. But it takes some time. So after getting about exact resonant frequency, then we can go for all those monitors. We can reduce the time of the simulation. Okay. Next. So it will display about the template name. Antenna underscore planar underscore 2. Which is the So we are getting workflow. So first what we have to select? We have to select about the substrate. Substrate it having the length of 110 meters, 110 millimeters, and height will be width will be 100 millimeters. So go for modeling. We're having different shapes. So brick, sphere, core, torus, cylinder. In that we are having circular elliptical. So we can go for extraction for irregular shape. For go for face and aperture for feeding. For threading we can use these symbols. So what we have required, we require the brick. Either we can make double click or we can press escape. So this is substrate. We have to mention the width and height. So we can choose width will be minus W by 2 to W by 2. Later we can fix the W value. Okay. Length will be minus L by 2 to, otherwise we can choose 0 to height. Substrate height will be 1.6 mm. Substrate height will be 1.6 mm. We can choose minus H by 2 to H by 2.